Today I want to walk you through computer vision from first principles, assuming you are technically sophisticated but want to ground your understanding of how machines actually interpret and analyze visual information. Computer vision is, at its core, the attempt to transform raw visual signals into structured, meaningful representations that can support decision-making. It is about turning pixels into concepts. Let us begin with what an image actually is from a machine's perspective. A digital image is a grid of numbers. In a grayscale image, each pixel contains a single intensity value. In a color image, each pixel usually contains 3 values corresponding to red, green, and blue channels. If you have a 224 by 224 RGB image, that is 224 times 224 times 3 numbers. That is over 150,000 scalar values. To a machine, that is the starting point. There is no inherent notion of edges, shapes, or objects. There is only a structured array of intensities. The first challenge in computer vision is that the mapping from pixel space to semantic meaning is highly nonlinear and highly invariant. If I show you a cat in bright sunlight and then the same cat in shadow, you recognize it as the same object. If the cat is rotated, partially occluded, or viewed from a different angle, you still recognize it. Pixel values change dramatically under these transformations. Yet human perception remains stable. The goal of computer vision systems is to learn representations that are similarly invariant to irrelevant changes while remaining sensitive to relevant distinctions. Early computer vision approaches relied heavily on hand-engineered features. Researchers designed edge detectors, corner detectors, texture descriptors, and shape features. The idea was to extract mid-level representations that were more stable than raw pixels. For example, Sobel filters approximate gradients in the image and highlight edges. Histogram of oriented gradients captures distributions of local edge orientations. These methods worked reasonably well for constrained tasks, but they required significant domain expertise and did not scale gracefully to the complexity of real-world visual scenes. The transition to modern computer vision began with the rise of deep learning, particularly convolutional neural networks. A convolutional neural network is designed to exploit the spatial structure of images. Instead of connecting every input pixel to every neuron in the next layer, convolutional layers apply small learnable filters that slide across the image. Each filter looks at a local region, such as a 3x3 or 5x5 patch, and computes a weighted sum. The same filter is applied at every spatial location. This weight sharing dramatically reduces the number of parameters and encodes the assumption that local patterns are useful everywhere in the image. This design reflects an important inductive bias. We assume that edges, textures, and small patterns are meaningful building blocks, and that their significance does not depend on absolute position. A vertical edge on the left side of an image is detected by the same filter as a vertical edge on the right side. This translation invariance is built directly into the convolution operation. As you stack convolutional layers, something interesting happens. Early layers tend to learn simple features such as edges and color contrasts. Middle layers learn combinations of edges forming shapes or textures. Deeper layers learn object parts and eventually whole object representations. This hierarchical feature learning mirrors, in some abstract sense, the processing hierarchy in biological visual systems. Pooling layers are often inserted between convolutional layers. Pooling reduces spatial resolution by summarizing local neighborhoods, typically through max or average operations. This serves 2 purposes. First, it reduces computational load. Second, it increases invariance to small translations or distortions. If a feature shifts slightly, pooling ensures the representation remains relatively stable. At the end of a convolutional network, the spatial feature maps are typically flattened or globally pooled to produce a fixed-length vector. This vector can then feed into fully connected layers for classification. In image classification tasks, the network is trained with labeled images. The loss function compares predicted class probabilities to true labels, and gradients update all filters and weights. Over time, the network learns filters that extract features useful for discriminating between classes. It is important to recognize that the features are not manually specified. They are learned. The loss function shapes the internal representations so that images of the same class cluster in representation space and images of different classes separate. The network effectively learns a feature extractor tailored to the classification objective. Image classification is only one task in computer vision. Another fundamental task is object detection. Instead of assigning a single label to the entire image, object detection aims to locate and classify multiple objects within an image. This requires predicting bounding boxes along with class labels. Architectures for detection extend classification networks by adding components that propose candidate regions and refine their coordinates. Training involves not only classification loss but also regression loss for bounding box coordinates. Semantic segmentation goes even further. Instead of predicting boxes, it assigns a class. The output is a dense map the same size as the input image. This requires preserving spatial information throughout the network. Architectures often use encoder-decoder structures. The encoder compresses the image into deep features, and the decoder upsamples these features back to full resolution, combining coarse semantic information with fine spatial detail. All these tasks share a common pattern. The system takes raw pixel arrays and transforms them through a series of learned operations into increasingly abstract representations. The early representations are local and low-level. The later representations are global and semantic. Training aligns these representations with task objectives. In recent years, transformer architectures have entered computer vision. Vision transformers divide the image into patches, flatten each patch, and treat it as a token in a sequence. These tokens are projected into embedding vectors and processed by self-attention layers. Self-attention allows each patch to interact with every other patch, capturing global context from the beginning rather than relying solely on local convolutions. This shift is significant because it reduces reliance on handcrafted inductive biases. Convolutions assume locality and translation invariance. Transformers are more flexible but require larger datasets and more computation to learn appropriate invariances. In practice, hybrid models combining convolutional stems with transformer layers often perform well. Another key area in computer vision is representation learning without full supervision. Labeling images is expensive. Self-supervised learning aims to learn useful visual representations without requiring human annotated labels. One approach is contrastive learning. The model is trained to produce similar representations for different augmented views of the same image while pushing apart representations of different images. Data augmentations such as cropping, color jittering, and flipping are applied. The network learns invariance to these transformations because the training objective enforces it. Self-supervised learning demonstrates that much of visual structure can be learned from the data distribution itself. The model learns to encode shapes, textures, and object-level features because these are stable across augmentations. Once trained, the representation can be fine-tuned for specific tasks with fewer labeled examples. Let us consider what makes vision particularly challenging compared to other domains. Visual data is high-dimensional and continuous. A small change in viewpoint can dramatically alter pixel values. Lighting conditions introduce variability. Objects can occlude each other. The mapping from three-dimensional scenes to two-dimensional images is a projection that discards depth information. Yet humans effortlessly infer depth, motion, and object permanence from sequences of images. To address depth, computer vision systems use techniques such as stereo vision, where two images from slightly different viewpoints are compared to infer depth through disparity. More recently, neural networks are trained to estimate depth from a single image by learning statistical cues associated with depth in large datasets. Motion analysis introduces temporal structure. In video, frames form a sequence. Models must capture both spatial and temporal dependencies. Architectures for video analysis may use 3D convolutions that operate across space and time, or they may combine convolutional feature extractors with recurrent networks or temporal attention mechanisms. Another important topic is generative modeling in vision. Instead of mapping images to labels, generative models aim to model the distribution of images themselves. Variational autoencoders, generative adversarial networks, and diffusion models learn to generate realistic images. These models require learning detailed representations of visual structure. Generative modeling provides insight into how models internalize patterns of texture, shape, and global composition. In practical applications, computer vision systems power autonomous vehicles, medical imaging diagnostics, facial recognition, industrial inspection, and augmented reality. In autonomous driving, the system must detect pedestrians, vehicles, traffic signs, and lanes in real time. It must interpret scenes under varying weather and lighting conditions. The reliability requirements are high, and errors can have severe consequences. In medical imaging, vision models analyze X-rays, MRIs, or CT scans to detect abnormalities. Here, subtle visual cues may be critical. The models must be sensitive to small anomalies while avoiding false positives. Interpretability and calibration become especially important. As systems become more capable, concerns about bias and fairness arise. If training data is not representative, models may perform poorly on underrepresented populations or conditions. For example, facial recognition systems have historically shown disparate performance across different demographic groups. This highlights the importance of data diversity and careful evaluation. Robustness is another major issue. Small perturbations to images, sometimes imperceptible to humans, can cause neural networks to misclassify with high confidence. These adversarial examples reveal vulnerabilities in learned representations. Research into robust training and defense mechanisms continues, aiming to align model perception more closely with human perception. When you analyze computer vision systems, it is helpful to think in terms of representation, invariance, and objective. Representation refers to how the image is encoded internally. Invariance refers to which transformations leave the representation stable. The objective defines what the model is optimized to do. The interplay among these factors determines system behavior. At a deeper conceptual level, computer vision is about building a hierarchy that bridges from raw sensory input to abstract concepts. Pixels become edges. Edges become shapes. Shapes become objects. Objects become scenes. Scenes become semantic interpretations. Each layer in a deep network approximates one step in this hierarchy, though not always in a clean or interpretable way. We should also acknowledge that vision does not operate in isolation in intelligent systems. Humans integrate visual information with language, sound, and prior knowledge. Modern AI systems increasingly do the same, combining vision with language models to answer questions about images or generate captions. But even in multimodal systems, the visual encoder remains responsible for extracting structured information from pixel arrays. In summary, computer vision is the discipline of enabling machines to interpret and analyze visual information. It transforms grids of numbers into structured representations through learned hierarchical models. Convolutional networks introduce strong spatial inductive biases. Transformers introduced flexible global reasoning. Self-supervised learning reduced reliance on labels. Across tasks such as classification, detection, segmentation, depth estimation, and generation, the unifying theme is representation learning, discovering internal vector spaces where visual patterns are organized in ways that support reasoning and decision-making. Understanding computer vision means understanding how these representations are built, how they encode invariances, how they are shaped by objectives and data, and how they generalize beyond training conditions. When you look at an image, you see objects and meaning. When a machine looks at an image, it sees numbers. Computer vision is the science and engineering effort to close that gap by learning the right transformations from numbers to meaning.
If you find this video exciting, please like, subscribe, and turn on notifications. See you in the next AI for Beginners educational video.